I have the graph in here.
How would you figure out theta?
We'll get there.
Okay.
All right, so I'm assuming that all of you can see this. I've got three different lines here. I got a blue one that's curving up like this, a red one that's going straight, and a green one that's curving sort of down. The red one is just theta. The blue one is tan of theta, and the green one is sine of theta. So notice how there's a large overlap here between the three functions.
Yeah.
And matter of fact, tan breaks away first, and sine stays on a little bit longer, but they seem, there's a lot of overlap there, with theta being somewhere around 0.25 or so. There's a lot of overlap. As a matter of fact, you are 10%, where, I got it in here somewhere. At a 30-degree angle, tangent is 10% off. And I feel like I'm missing a page here. And sine is 10% off, somewhere around 40 degrees. Oh, there we go. Sine is different from theta at 40, just shy of 44 degrees, and it's 5% off at 31 degrees. Typically, the much less than is if you're under 10%. So if it's 0.1 or less. So this now equation becomes g theta is equal to negative r alpha. I now have a relationship here relating some position, angular position, with its acceleration. And I have a whole set of rules that we've already derived that I can just plug into. I know that the period is 2 pi times the square root of m over k. Assuming that we have kx is equal to negative. I don't think I wrote that explicitly before, but it's implied from the fact that it's the reciprocal of the frequency. Well, in this, over there, what we have over there, I have g theta is equal to negative r alpha. R is just the length of the pendulum. So I'm actually going to put an L there. Paralleling this, we get t is equal to 2 pi times the square root of, well, instead of k, we have g. Instead of m, we have L. And so now we have a formula for the period of a simple pendulum. And this is a major step. We now have a method of timing. Historically, major step. Galileo, supposedly in church, noticed the chandelier swaying back and forth, and he noticed the period was about the same regardless of the amplitude. He recognized that he now had a way, well, think about it, if I can figure out how long I need to make a pendulum for a 1 second pendulum, so it goes back and forth in 1 second, I now have timing down to, well, that's 1 second all the way there, so it's a half second halfway, quarter of a second to here. So I can get some timing down to basically a quarter of a second.
Oh, like in clocks?
Yes. Grandfather clocks work under the same idea, that things got the pendulum swinging back and forth. Yeah, sorry about that, BJ.
It's fine. How come those don't stop?
You'll have to reset them.
You have like a weight
I
or
do.
something.
Yeah, the one that we had a weight on it.
Ours has 3.
Ah, And if time is off, well, I have two different ways of changing it. The way that, assuming I'm not gonna change the acceleration due to gravity, I can change the length of basically the weight that's of the pendulum. Move it down, move it up if I need it to go longer, slower. And I found for the clock that we have, it was incredibly difficult to do. No matter how we adjusted it, it was still off.
So L's the length of it.
And G is the acceleration due to gravity. So if you have a grandfather clock perfectly timed for here, you go up into the mountains, it's gonna be a little bit off because G has changed.
So they're very finicky.
Yeah.
Would you need
By
to
periods.
account for that by changing the length a little bit?
Yeah.
Ah.
So let's figure out what the length is for a period of 1 second. Assuming we're here at Winston-Salem, 9.798 meters per second squared is the acceleration.
Well, that's why you put that in all of our, that's why you put that in all of our labs, that number. I thought.
Yeah, that is for Winston-Salem. Wrote that, I probably, instead of writing A with a vector symbol, I should write G equals.
How much does little G how much does it fluctuate across the United States, do you know?
Death Valley has the largest in the US, I believe. It's 9.76 going off of memory. And
There's a video where he like, that was, isn't the North or South Pole like?
Is that 798 you said?
9.798.
I think the North or South Pole is like 9.82 or 9.83.
Something like that. Trying to see if I have the numbers here or if it's sitting in my office. Yeah, I think it's in my office. But, I mean, the fluctuation, the average, world average is 9.806, I think. So probably at most of the extremes, .005 meters per second squared. That would be 0.01 meters per second squared, that feels right. It's not a big difference, which is why so many problems get away with just, not what needs, good enough.
Yeah, they see that on some physics problems, it's 60, 9.8.
All right, so what do we have for L?
24.17.
I will back that up.
24.17 what?
Meters.
Oh, is that centimeters?
Units of measurement.
24.17.
Got .2481 meters.
That would make more sense, but don't forget the 2 there. I knew it was about 24 or 25 centimeters. That's why I was thrown off by the other one. So I've had a string that's, well, roughly that length span of my hand. I now have a timing device.
So did he invent the clock?
Say it again?
Did he invent the clock?
I don't think so. I don't know, I'm not quite sure the order in which that happened. Maybe Galileo did.
Is that
Seemed
not
like-
isn't that how the first clocks were though, or no?
Or the first clocks were sundials.
Yeah.
I always think that the Swiss did it, but it probably was all about the same time. I don't know about who influenced whom and in what order. Or maybe the story of him figuring this stuff out in church was a lie. All right, questions to hear?
That was very interesting.
instead of listening to church, he was doing physics wrong.
I've been in many a service where that was preferable. Though I was in one where after the minister gave the sermon, got a standing ovation. I don't even remember what the topic was. Overall, the guy was generally incredibly boring, but he nailed it that day. All right, I think we're done at 3:20. So I'm gonna say that's close enough for now, so. I will see you on Zoom tomorrow.
That was interesting. I did not know that like clause.
I know there was a difficulty because finding the latitude that you're on is incredibly easy based on the stars. Finding longitude was a lot more difficult, and it wasn't until they were able to produce a clock that could maintain consistency as you go across the ocean that they could figure out where they were longitudinally. So if you look at old maps and how distorted they are, generally they're spot on latitude-wise, not longitude-wise.
When is test 1B corrections due?
End of the semester.
Yep. Friday of next week.
Okay.
Oh, how do you want me to turn those in?
Take pictures and submit it. They're